Okay, this is section 6.2, day 1, and we are on the first day of learning how to do integration by substitution. So the essential question for today is, how is substitution used to make integration easier? So just a quick grammar lesson here. Substitution, okay, it's the action of replacing someone or something with another person or thing, right? So for instance, when I am not in the classroom, there's a substitute there to take my place. So how can we use that to make integration easier without getting rid of me? That's a joke. So before we jump into it, just a quick comment on trigonometric integral formulas. So we know that integration, or anti-differentiation, is reversing the differentiation process. So if you remember taking the 6 derivatives, if we look on the right-hand side of these expressions, sine, cosine, tangent, cotangent, secant, and cosecant, we got our derivatives, right, our little f's. So when we do anti-differentiation, when we work backwards, notice we start out with all the derivatives we found last fall. So if you look at all of 6 of these, we never integrate or anti-differentiate secant, but we do anti-differentiate secant squared because we know that's a derivative for tangent squared. And we never take the antiderivative of just a tangent, but we do take the antiderivative of secant tangent because we know that this secant tangent is the derivative for secant. So the antiderivative of secant tangent must be just secant. So we very strictly reverse those differentiation rules to get antiderivative rules for our trig functions. So before we jump into the notes, this is just for a discussion. This is kind of an overview of what this day is about in terms of substitution. So for instance, today, this is what we're going to see. And let's compare that to what we already know how to do. So for instance, today we're going to see things that look like this. Now, it would be really nice if it would just look like this. We know how to do the antiderivative of x to the 5th, but we don't know what we have to do when it's more complicated than just x. Today we're also going to see something that looks like that. Now, if it looked just like this, just root x, again, we could say that that's an x to the half power, and we could do the antiderivative here, but here looks just slightly different. Today we're also going to see something that looks like this. Now, if it were just cosine x, you would be, off and running and doing the antiderivative. This looks a little bit different. We're also going to see stuff that looks like this. It would be really nice if it just looked like this. And we're also going to see stuff that looks like this. This will be the first example for tomorrow. What would really be nice if it just looked like this, right? Then we could just do x to the negative half and do an antiderivative. But the really nice thing is all of these, this has a really close connection to this, and this has a really close connection to this. So all of these things, if we do what we call a U sub, and that's a substitution process, we can get them to look like this, and then that makes the integration much simpler. Now, this whole description of what a U sub is, and I'll get into the reason why we call it a U sub, but it's just substitution. This might look a little overwhelming, and we'll kind of scratch the surface of what we see here in the integrand part. Remember, the integrand is all of this stuff between the integral symbol and the dx, the dummy variable. So in the integrand here, we'll keep coming back to this expression and work with it a little bit for the next couple of days. But notice that we're starting to get into anti-differentiation, where we have in the integrand a nested function. So we have an f of g of x, where we have a function inside something else. And so if you remember back to last fall when we were dealing with inside and outside functions, we were using the chain rule to find derivatives. So U subs, or substitution, is the reversal of that chain rule process. So what we're looking for in the integrand here is a nested function. And then we're looking for the derivative of that nested function. Okay? And those are critical components to have that to let us know that a U sub is the thing to do. Now, this might sound a little silly, but we have an 8-step process here. And this process will see us through every problem that we need to do. So have faith in this process. It'll work. Okay, what happens is when things get really ugly is when we stop paying attention to this process. So we're just going to really be very vigilant here about making sure we're doing every step in the process, and things will work out. So let's take a look at this first expression. Okay, we want the antiderivative of 3x squared to the 5th power. So if you look back, and that 8-step process is in your notes. So if you look back at those 8 steps, that first step, and I'm going to ask you this over and over, the first step is to identify the expression that you want to remove. So here's what we're starting with. And so when I ask you to identify the expression that you want to remove, what I'm asking you to do is look at the integrand and find brackets or square root signs, something that's giving you the indication that you have an inside and outside function, some sort of grouping sign. And so we can see that we have an inside function here. So that's what we want to remove. Step 2, set the expression equal to u. So take this and set it equal to u. U equals this. And like I said, we're going to follow these steps, and we're just going to keep doing them over and over, and they're going to become second nature by the end of this class period. Step 3, we're going to differentiate u. So if you notice, we're taking the derivative here. Okay, so this whole process of when we call this a u sub for this reason. We use the variable u. And that's really the only reason why we call it a u sub. You can just call it substitution if you want to. Okay, so we have to differentiate this and so that we can set up some substitutions. So the derivative of this, du dx, is 3. And then step 4, we say solve for dx. So we got to solve this. We got to rearrange this stuff. So we're going to think of this as du dx equals 3 over 1. And this Leibniz notation, we can deal with that much like we deal with a fraction. So we're going to cross multiply. So du times 1 is du, dx times 3 is 3 dx. So du equals 3 dx, and I need to solve for dx, that dummy variable. So I'm going to divide each side by 3, and I'm going to get 1/3 du equals dx. Step 5, substitute the u, that's this, and the dx, that's this, into the integral. So when we look at this expression here, we're going to keep the integral symbol. We're going to keep the brackets. We're going to, instead of having this here, we're going to have u there. We're going to keep this bracket, keep that power. And instead of having the dx, we're going to have the 1/3 du. So the substitution looks like this. Oh, I didn't use the brackets. That's okay. So I have my integration. I'm now calling this u because that's my substitution. And then I have to get rid of the dx. So this is my substitution. So I have those two substitutions. Now, you know the properties of anti-differentiation let you take these constants out front. So we're going to move to the 1/3 out front, and we're integrating u to the 5th du. That's much easier to integrate than this. So let's use our power rule here. Step 6, integrate the easy, this is an easier integral, so we're going to integrate the easier integral. So we have 1/3 times, bump up this power to 6, divide by the new power 6. So there's our integral, there's our antiderivative. So if you notice, this whole process has you taking a derivative of a substitute and then integrating or anti-differentiating something that's a lot simpler. So we took the antiderivative here. Step 7 and 8 I combine. So, oh yeah, I made this simpler. 1/3 times 1/6 is 1/18. Steps 7 and 8 I usually combine because I do them at the same time. I replace the u because we are being asked to find the antiderivative with respect to variable x. So we need an answer that has variable x in it. So I do these two at the same time. I replace this with my substitute, and then I put my plus c on since this is an antiderivative. So it's going to look like 1/18. Instead of u, it's 3x plus 2 to the 6th power plus c. And we're done. This is the antiderivative of this. If you wanted to take the derivative of this and do the chain rule inside, you would end up with 3x plus 2 to the 5th. Going on to the next example. Here's example 2. Now we have a radical. We're going to go through the same 8 steps. Okay, so step 1, identify the expression to remove. So here's the problem. And again, when I ask you to identify the expression to remove, we're looking at this integrand right here, and we're finding a grouping symbol, and we did. It's the radical. It's a square root sign. And we're looking at then the inside of that grouping symbol. That's our inside function. So there's the expression we want to remove. Step 2, and these are the same steps, doesn't matter what problem we're working on, set this expression equal to u. Step 3, differentiate that expression. So du dx equals 4. Step 4, solve for dx. So again, we're going to think of this as 4 over 1. So it's going to be 1 times du equals 4 times dx, or du equals 4 dx. We're going to rearrange this so that we solve for dx. We're not done here because dx isn't by itself. So divide each side by 4, we get 1/4 du equals dx. Step 5, substitute the u and the dx back into the integral. So we come back here, we're going to keep the integration sign, we're going to keep the radical because we didn't remove it. We're going to take this stuff out and call it u. And then the dx we're going to remove, and we're going to replace it with 1/4 du. Step 6, we're going to simplify this actually before we go on to step 6. We're going to pull that 1/4 out to the front because we can do that with constants. And notice what I did here. We have the square root of u, and some people can take the antiderivative of this just fine. I like to rewrite it with my fractional power. I'm kind of a very visual person, so I need to see that half power so I can bump that up by 1. So step 6, integrate the easier integral. This is definitely easier than that. So we're going to have our 1/4 times. Let's go ahead and use our power rule now. Bumping this up by 1, adding 1 to this is 3/2. And we're going to divide by 3/2. And we're going to write it just like that. Again, being the visual person that I am, I like to see this so that I can work out all of this stuff. Okay, so let's talk about what's happening out here with all these fractions. I've got 1/4 times, and then I've got 3 over 2 in the denominator. So 3 over 2 in the denominator is the same as 2 over 3 multiplying. So we have to think of this as 2/3 times 1/4, which is 2 over 12. And if we reduce that, we get 1/6. So this is 1/6 u to the 3/2 power. And then steps 7 and 8, I combine. I come back here, I see my u, and I replace it with this. And I put my plus c on the end. So it looks like that. Okay, remember this 3/2 power really means cubing this and taking the square root. So the radical still is very much a part of this answer. We're just expressing it as a power, a fractional power, instead of a radical. Okay, looking at the next example, we have cosine of 7x plus 5. Finding the antiderivative of that. We're going to go through the same 8 steps. Identify the expression to remove. So again, we're looking at our integrand. That's this information here between the integral symbol and the dx. And we're looking for grouping symbols, so either brackets or radicals. And so I see some brackets here. And so I know that this must be my inside function. So that's what we're going to remove. Step 2, set that equal to u. So I'm going to let u equal 7x plus 5. Step 3 is take the derivative of that. So du dx equals 7. Step 4, solve for dx. So again, I'm going to think of this as 7 over 1. So I'm going to have 1 times du equals 7 times dx. And I still haven't solved for dx quite yet, so I'm going to divide each side by 7. So I have 1/7 du equals dx. Step 5, I'm going to take this expression and substitute in u and substitute the dx and get a simpler expression. So I now have, instead of this, I have cosine u, and instead of dx, I have 1/7 du. And then I'm going to use my properties to bring my 1/7 out front, and I have a simpler integral. This is definitely simpler than that. So I'm integrating cosine u du. So for step 6, I'm going to go ahead and integrate or antidifferentiate. So I'm going to have 1/7, and the antiderivative of cosine u is sine u. And then my combo here, 7 and 8, I'm going to replace my u with my x variable substitute, and I'm going to throw on my plus c. So we end up with 1/7 sine 7x plus 5 plus c. Okay, so for the next example, this is looking a little bit different than what you have on your paper. And so I want you to kind of take a second to look at what you have on your paper and what we have here. So in your paper, the power 4 is between the sine and the x. And so that means the same thing. When we have a power here, it means that we're taking the trigonometric function to a power. And so we can have the power here without the brackets, or we can use brackets and we can put the power out here. So this means literally sine x times sine x times sine x times sine x. And so this expression, it's easier to see the grouping symbol, and it's easier to see the inside function. So when we identify the expression to remove, you have to think of what you have on your paper as actually having brackets around that function. So we're going to remove sine x. Don't worry about this right now. Have faith in the process. It's going to work out. 2, set that expression equal to u. So I'll let u equal sine x. Step 3, differentiate that expression for u. So du dx equals the derivative of sine is cosine. Step 4, solve for dx. Now this gets a little weird looking, but have faith in it. We're going to think of this as cosine x over 1. We're going to do the exact same thing we've always done in the last 3 examples. So this is cosine x over 1. Then we have 1 times du equals cosine x times dx. Okay, we're just doing the same cross multiply. We just, don't let this throw you for a loop. This is just like the numbers we had in the earlier examples. Now, I haven't quite solved for dx, so I'm going to divide by cosine. So I get dx equals du divided by cosine. We need this. Don't think that this is in the wrong spot. It's in the right spot. We really need this, and you'll see why in the next step. Step 5 is substitution, right? So we're going to substitute in the u. So instead of seeing this here, we're going to see a u, and we're going to substitute the dx. So instead of seeing this here, we're going to see this. What I want to point out, though, is that we're not doing anything with this right now. It's here right now, and it's going to appear here when I click. Okay, so we've got our u to the 4th power. Our dx, we've got our du over cosine x. And we didn't touch this. We had nothing to remove, to put in its place, so it stayed. And notice, though, what's happening here. And that's why I said we're really going to need this cosine in the denominator. We set up a situation with this substitution where this cosine and that cosine are going to cancel. And that will happen every time. That will happen every time. If we end up having some sort of x term over here, it will end up canceling. Okay, because again, and this gets back to that substitution definition that I said we're going to kind of keep coming back to, is if we had the expression that says f of g of x times g prime of x. If you look back at that box on the top of the page, so this is my g of x, right? That's my inside function. And here's my g prime. That's my derivative of my inside function. And when we have that relationship here, we can get this canceling to occur every time. So we're looking for a function and its derivative. We know we can do a u sub, and that's going to end up canceling. So I'm going to rewrite this now. And after I did that canceling, the simpler integral looks like that, which is a lot simpler than this. So we're going to go on to step 6 and take the antiderivative of this. So we can use our power rule. We're going to bump up that power to 5 and divide by the new power, 5. And then we're going to do our 7-8 combo here, step 7 and step 8. We're going to take the u and replace it with its original expression. So this is going to be sine to the 5th power divided by 5 plus c. And like I mentioned up here about the presence of brackets and with powers, we can take that 5 and slide it next to the sine function and do away with those brackets. So you probably will see this expression more like this. So at this point, you should be able to get a good start on this homework. And if you're looking for a proficiency quiz, I would wait until after the 3rd day to take that.